Welcome to the next session of finite automata. In the previous sessions, we already discussed regular grammars, regular expressions, and regular languages. In the current session, we are going to discuss about classification of regular grammars. Classification of grammars. The classification was done by a person known as Chomsky. So it is known as Chomsky's hierarchy or Chomsky's classification of grammars. Abraham Noam Chomsky is born on December 7, 1928. After several decades, Chomsky is credited with the creation of the theory of generative grammar, generative regular grammar. It is considered as one of the most significant contributions to the field of linguistics made in the 20th century. Noam Chomsky published syntactic structures. He defined a classification of formal languages in terms of their generative power, known as the Chomsky's hierarchy or Chomsky's classification of grammars. Any language is a structured medium of communication, whether it is a spoken or written natural language, sign or coded language, or a formal programming language. Languages are characterized by two basic elements. The first one is syntax. It means that grammatic rules. And the second one is semantics, the meaning. In some languages, the meaning might vary depend upon a third factor that is known as the context of usage. Depending on restrictions and complexity present in the grammar, regular languages find a place in the classification done by Chomsky. Classification done by Chomsky. Noam Chomsky, celebrated American linguist cum cognitive scientist, he defined this hierarchy. He classified these grammars in 1956. It is also known as Chomsky hierarchy or Chomsky classification of grammar. Although this concept is quite old, there is renewed interest because of its relevance to natural language processing, theory of computation, development of compilers or design of compilers in finite automata and systems of. It helps us to answer questions like, can a natural language like English be described? Whether it can be parsed, whether it can be compiled with the same methods as used for artificial programming languages or formal programming languages in computer science. According to Noam Chomsky, there are four levels, four types of grammars. Type 0, Type 1, Type 2 and Type 2. type 0, type 1, type 2 and type 3. With every level, the grammar becomes less restrictive in rules but more complicated to automate. Type 0. Type 0 grammars. Type 0 grammars are also known as recursively enumerable grammars. Recursively enumerable regular grammars. They generate recursively enumerable regular languages. They are too generic and unrestricted to describe the syntax of either programming or natural languages. The productions have no restrictions, so it is known as unrestricted grammar. Unrestricted grammar. Here, they generate the languages. They generate the languages that can be automated by a Turing machine or recognized by a Turing machine. It is the most popular grammar. Type 0 regular languages have no restrictions on their grammar and may loop forever. They do not have an algorithm enumerating all the elements. Non-computable functions exist in mathematics and computer science. Type 0 application or automation is Turing machine. The Turing machine, however, allows representing even such functions as a sequence of discrete steps. Control is finite, even if data might be seemingly infinite. It is an abstract machine. Turing machine is an abstract model. Type 0, languages with no restrictions, is not conducive to communication or automation. Hence, there are no common examples for this type. But we can consider an example. Small a, capital A, B generates small b, capital B. Small a, capital A generates epsilon. The productions can be in the form of alpha generates beta. Alpha is a string of terminals and non-terminals with at least one non-terminal, and alpha cannot be null. Alpha cannot be null. Beta is a string of terminals and non-terminals. Then what is the terminal? Terminal is the smallest unit of a grammar that appears in production rule. It cannot be further broken down. Then non-terminals are symbols that can be replaced by other non-terminal symbols or terminal symbols by successive application of production rule. Then what is meant by a production rule? Production rule or production rules are set of rules for every grammar describing how to form strings from the language that are syntactically valid. We already saw what is a terminal, non-terminal and production rules in case of regular grammars. Here in type 0 grammar, they are recursively enumerable grammars. They have no restrictions, so they are also known as unrestricted grammar. Its application is in the automation of Turing machine. Then second one, type 1 grammar. Type 1 grammars are known as context sensitive grammar. Context sensitive grammar. The highest programmable level, they generate context sensitive languages. Type 1 grammars generate context sensitive languages. If we apply some restrictions on type 0, in the previous type 0, if we apply some restrictions, we can obtain this type 1 grammars, context sensitive grammars. Here the length of alpha must be less than or equal to beta. The productions must be in the form alpha A beta generates alpha gamma beta, where A is an element of n, that means A is a non-terminal, alpha, beta, gamma, elements of terminal union non-terminal. The string of terminals and non-terminals. The strings alpha and beta may be empty. Gamma must be non-empty. The languages generated by type 1 grammars are recognized by linear bounded automation. So, context sensitive grammars have rules of the form alpha A beta generates alpha gamma beta. Alpha A beta generates alpha gamma beta. Moreover, type 1 languages place the restriction on productions alpha generates beta of a phrase structure that beta be at least as long as alpha. They become context sensitive. They permit replacement of alpha by beta only in a context. Context alpha, context generates context beta, context generates context beta. The length of alpha must be less than or equal to beta. The length of alpha must be less than or equal to beta. These languages generated are recognized by linear bounded automation. It is a form of restricted Turing machine, which instead of being unlimited, it is bounded by some computable linear function. Linear bounded, computable linear function. The advantage of this automation is that its memory requirement is predictable. Even if the execution is recursive, the upper limit of random access memory can be predicted. The memory requirements is predictable. Then comes to the next grammar, type 2 grammar. Type 2 grammars. They are known as context-free grammar. Context-free grammar. Type 2 grammars generate context-free languages. They generate context-free languages, a category of immense interest to natural language processing. Is context-free languages. Here all rules for productions must be in the form of A generates gamma. A generates gamma. A element of non-terminal, gamma element of terminal union non-terminal means this family of or the set of string of terminals and non-terminals. Moreover, they are capable of handling an important language construct called nested dependencies. Nested dependencies. We already know what is meant by nesting. We know nesting of loops, nesting of operations. They are nested dependencies. In programming languages, the matching of parentheses of functions or loops get covered by these context-free grammars. Context-free grammars. Moreover, these languages generated by the type 2 grammars or context-free grammars are to be recognized by a non-deterministic push-down automata. Push-down automata is the application. In order to match nested dependencies, we need a stack. We need a stack. So, push-down automata is the application of type 2 grammars or context-free languages. This automation requires a one-ended memory stack. One-ended memory stack. That end is known as top of the stack. For instance, to match the number of if and else phrases, the automation needs to remember the latest occurring of if statement. Only then it can be find the corresponding else statement. So push down automata, non-deterministic push down automata is an application of type 2 grammars. Type 2 grammars are known as context-free grammars, or they generate context-free languages. What is the context? Here I represented with an example. Small a, capital A, B generates BB. The left context of capital A is small a, and the right context of capital A is, if P is like epsilon A epsilon, the production rule is like epsilon A epsilon, left and right are epsilon. We are freeing this variable from any context. Examples such as S generates XA, XA generates A, X generates AX, X generates ABC, X generates epsilon. A set of production examples can be represented in case of type 2 grammar. Then moving to type 3 grammars. What is meant by a type 3 grammar? Type 3 grammars are regular grammars. They generate regular languages. The last section will be discussed about regular grammars and regular languages. More restrictions on type 2. Type 3 grammars must have a single non-terminal on the left-hand side and a right-hand side consisting of single terminal or single terminal followed by a single non-terminal. The productions must be in the form of x generates small a or x generates small a y. X, Y elements of non-terminal, the capital letters denotes the non-terminals and small letter denotes the terminals. Small a element of terminal. Here the rule S generates epsilon is allowed. S does not appear on the right hand side of any rule. Most restrictive of this set. They generate regular languages. They are regular grammars. They must have a single non-terminal on the left-hand side and a right-hand side consisting of single terminal or single terminal followed by a single non-terminal. Type 3 grammars. We don't classify entire languages as the production rules are restrictive. However, under type 3, constructs inside a language describable by regular expressions come under this step. Rule for naming an identifier in a programming language is an instance, it is an example of type 3 grammars. Regular expressions with any combination of case insensitive letters, some special characters, some numbers, as we start with a letter, these all can be considered as an example of type 3 grammars or regular grammars. While considering the application, finite state automata. Finite automata. To compute constructs for a regular language, the most important consideration is that there is no memory requirement. There is no memory requirement. The examples, x generates epsilon, x generates small a or x generates small a capital Y generates small b. Here small b denotes terminals. Epsilon is an empty string, capital X and capital Y denotes non-terminal. Then take a look at the following illustration. What is the scope of each type of grammar? The diagram represents the scope of each type of grammar. The scope of each type of grammar. Recursively enumerable grammar, the type 0, context sensitive grammars, type 1, context free grammar, type 2, and regular grammars type. The containment of type 3 regular grammars is a subset of type 2, that is context free, which is a subset of type 1, that is context sensitive, which is a subset of type 0, that is recursive enumerable. How these differ from each other? We already discussed it. It is summarized in a table representation. Chomsky's classification of grammar based on grammar type, grammar accepted, language accepted, and automation. It is summarized in the given table. Type 0 grammars are unrestricted grammars. The languages are recursively enumerable languages. Moreover, the automation can be on Turing machine. Type 1 grammars are context sensitive grammar. The language accepted is context sensitive language. The automation is linear bounded automation. Type 2 grammars, they are context free grammar. The language accepted is context free language and the application is push down automation. Type 3 grammars are known as regular grammars. The language accepted is regular language and the automation is finite state automation. So, the most famous classification of grammars and languages introduced by Noam Chomsky, it is known as Chomsky's classification of regular languages or Chomsky's classification of regular grammars. Okay, thank you.